science. Yeah, we first met last spring, and he came to talk to me about some of his theories, and then he brought by demonstration after demonstration after demonstration. Some of the same demonstrations I think maybe I see here today.
Yes, some of them. Yeah.
Right, and these demonstrations really are wonderfully prepared, extremely pedagogical, helping, I hope you all to understand some things about physics that you may not have understood before. I think perhaps most impressive is his enthusiasm for science and for physics in particular. Also, I was incredibly impressed with his knowledge of the history of physics and how he can tell us about where some of the physical laws that we'll be studying in class come from. Without further ado, I hope that he'll continue to introduce himself and to introduce to us these very interesting experiments that he's brought.
Yes, thank you very much. My name is Vahan, Davoudian, and I graduated in electronics in 1978. I've done a lot of experiments in physics, so I just want to thank Dr. Gray and the Regis University, and especially you, the student. And I think Dr. Gray has a special personality. He's listening to the students, and I won't be surprised if one day he gets a Nobel Prize because he's researching a lot about the science. And I have seen him, he's so dedicated, he loves the student, and even after hours he stays here and just helps the student. And hopefully one day I will be able to repay kindness. Today we are going to demonstrate Earth's rotation. You might have seen some of these experiments, but the way I explained, no one has ever done in the history of science. Like this one, I am weighing the air molecules. So I will show you exactly how it works and in more details. And I will exactly explain why there is no perpetual motion. You may wonder why there is no perpetual motion. The reason why, anytime you have a moving object like a pendulum, is moving air. So in other words, in the technical work, is doing some work. So that work, I'm going to demonstrate exactly how it works. In order to understand how the Earth is rotating, you have to know so many laws of physics. But what I did, I simplified everything because I know conceptually it's not easy to understand. So in other words, in physics we call it counterintuitive. So in order to understand how the Earth is rotating, you have to know so many things. First of all is the Coriolis effect. That is so important. What it means, anytime you have a moving object on an accelerating frame of reference, or in other words, rotating, it deflects. That's the whole idea. And the second one is the most important one, is called inertia, which is the first law of motion. Objects in motion tends to stay in motion, object in stationary state. But the inertia is so important. What he did, Mr. Foucault, he was a great physicist. He did 3 experiments. The first one was only 7.5 like this building, but he used 5 kilograms, bulk or the weight. And then he realized that it's not going to work. And then the second time he used 36 feet floor, again 5 kilogram mass. And then he realized that he needed more inertia. So in other words, I will explain exactly what the inertia is. The last time he used 220 feet, which was huge. And imagine, the more your pendulum goes, at the same time the Earth under is rotating. That's the way you can see better. So I had to devise this ramp. Well, of course, this is almost like Galileo's ramp. But that is showing you exactly why we need more mass, why we need more period. So each time the arc, one arc is 1 period, back and forth is 1 period. So first of all, I want to show you, you have to know that those, and then you have to know exactly what the relativity is. Please don't confuse this with the, Albert Einstein or Mr. Henrik Lorentz, because those are so complicated. Mr. Galileo's is so easy. It's one accelerating frame of reference said always, if you want to understand Earth is rotating, you have to have frame of reference. If you don't have a frame of reference, you won't be able. If you're in a car, right, and then they close the windows, you have the super shock absorber. You cannot tell whether you're moving or stationary. Well, of course, he did it in a different way. He did it by in the ship. And then he said you go underneath on a deck, and then everywhere is covered. You have no idea it's sailing or it's not moving. So what he did was fantastic. Now I'm going to demonstrate you guys how it works. But before I show you the pendulum, I have to give you some idea why Mr. Fogu used big pendulum. Look, this one is exactly 15 grams, but that one is 150 grams. If I raise this, look, it might go a few seconds because this has less inertia. At the same time, this is swinging, the Earth is rotating under it. But if I swing this one, which is 10 times more, this will swing forever. Well, of course, this is not. See? And it doesn't matter. The laws of physics works the same everywhere. Now I'm going to show you something else. See, this one has more This one has more inertia. It's exactly the same way. Exactly the same way. If I roll this, because this has more friction, this is going to stop immediately. Look. But the important thing is, while this is swinging, what happened? This is going away from the center of the Earth. It's so important. But here is exactly the center of the Earth. You see what happened? It's like few seconds. It stopped. See? And every time it rotates, because it's doing some work, because of the friction, what happened? Every time it goes back and forth, you have this one is there. See? It stopped. But this one is not going to stop. Because this one, look. See, now here is the center of the Earth, but here is away from the Earth. So what happened here? It has gravitational potential energy, but here, when it gets over here, it has a kinetic energy. Kinetic energy means motion. So anytime you have something in motion, it doesn't matter, your car, airplane, whatever is in motion, they call it kinetic. So in other words, the faster you move, the more energy you have. That's why you have seen the cars with like 100 miles per hour. If they hit something, the deadly consequences. The reason why it's just not easy to stop, because that is the most important law in physics. Inertia means lazy. Well, that's a Greek word anyway. I mean, when you're talking about inertia, means how hard it is to move something like this ball, say, it has inertia. Now, it's attracted to the Earth. It's not going to go further, but see, I can move this easy. But if I have a huge ball like that, I won't be able to move. I need more force. And then, force, mass times acceleration. So inertia is the measure of mass. It shows you how easy it is to move something and how hard it is to stop something. If something is in motion, you won't be able to stop. You can stop this easy, but you cannot stop the bowling ball. If the same speed, the train is coming to you, no way. It's exactly the same thing, but see, it has more mass. There is no way you can stop it. See how long that takes? It's exactly the same ramp, and it's exactly the same acceleration. So anytime I have something like this, I have energy. But if I have it over here on the floor, I don't have energy compared to the ground, right? Because when I raise it, it has to go back to the state of equilibrium. So in other words, that thing is doing the same thing. When I raise it over here, it's away from the center of the Earth. It has to go back. And this is very complicated mechanics. They call it Hamiltonian mechanics. It's always kinetic energy is converted to gravitational, back and forth, back and forth. But the most important thing comes here in equation is the thermodynamic. And I don't know why in the books they don't explain that. Thermodynamic is so important. The entire universe works with the second law. if I compare our sun with a glass of water, it's exactly the same concept. But in a sun, what we have is a nuclear fusion. Billions of tons is converted every day. And then what we get, maybe 1% of it we get as sunlight. But the rest, sun is going to die someday or run out of hydrogen, but it's going to be like maybe 5 billion years. But if I put that glass of water here, it's exactly acting like a sun. What has entropy? Entropy means disorder. It goes from hot to cold. There is no way that glass of water, boiling water, is going to go back unless if you add energy. So what happened here, this is going back and forth, is doing some work, and because of friction, what happened is stopping it. That's why we never have perpetual motion, never. Always you need energy. If you don't gas your car, what will happen? You stop somewhere, you have to get gas. So that's exactly how the solar system works, the entire universe works. So that entropy always in equation. So is my pendulum over there. When I swing that back and forth, so I devised my own ball bearing. It's a computer, very fine ball bearing. So those are going this way, back and forth. It can also rotate because I have two ball bearings almost in the right angle. But I am going to show you anytime that pendulum moves, is doing some work. And then it's amazing if you watch, each swing is a little bit smaller. If I take that same thing on the moon, it's going to work forever. The reason why there is no atmosphere. But again, in the moon, the gravity is 1/6. So the restoring force is going to be much less, but it doesn't matter because moon doesn't have the atmosphere. This pendulum won't stop, it won't immediately. It will go forever. It might even go more rotations than Earth. If I take it to Jupiter, what will happen? It has 2.5 or 2.6 times Earth gravity. Well, of course, there's no way we can go to Jupiter. It's just a gas anyway. But what I mean, it's always important that anytime you see a motion, it's followed by the second law, which is thermodynamics. Now I'm going to demonstrate to you guys how this works. So anytime we move something on Earth, it's displacing Earth. And this is a fantastic scale. It shows 1/10 of the gram. Look what will happen. When I swing this, you can tell this is displacing Earth. And this has been calibrated for Denver only. Because, you know, by the seaside, you have 14.7 atmospheric pressure, right?
Pounds per square inch.
Yes. But here in Denver, it's less. If you go to the top of the mountain, because it's less, Earth is less. But here, I'm not sure, maybe 12 point something. But anyway, this scale is calibrated. If I move the Earth, look, what will happen? Can you see it? You guys can come over, have a look, okay? See, I'm displacing air. See, when I'm displacing air, because the atmospheric pressure is calibrated on this, when I'm displacing air, what happens? This gets less gravity. You can even see the minus sign. So, what Mr. Foucault did, it was exactly the same size, but this is hollow. It doesn't matter. The mass doesn't make any difference at all. The point is how big the bomb is and how much Earth is going to display. Look, the faster it moves, the more displacement you can see. You see Dr. Gray 15 or 20 maybe, right?
Only 5 so far.
Or 5? Well, if I go faster, it will be more, see?
Right, okay, I'm as high as 20 now.
Okay,
45, 75.
Yeah, see? Because it's displacing Earth, and what happened, the gravity is affecting that. So this is a unique experiment is showing what Mr. Foucault did. He was displacing Earth, and then he was so smart to use 28 grams. And if I compare with mine, mine is 130 grams, 28 kilograms. Imagine how much mass they have. And like I showed you guys, it doesn't matter where the mass is, always is resisting acceleration. That is where the first law of motion is. would just go back and forth. Well, of course, I have one I show you, and then I made some photocopies. I give you one. So when it's getting smaller and smaller, it makes oval shape. And then what happened? That oval shape means that, at the same time your body is going back and forth, the Earth is rotating around it. It's a little bit not easy to understand, I know. But the point is, me, Dr. Gray, and all the students, we are traveling with the Earth. That's so important. See, we don't feel anything because all of us, we are traveling with the Earth. Now I show you here what I mean. See, you can think this as an Earth. It's half Earth. You can come close if you like. See, sometimes it's not easy for a student to understand why on North Pole there is no rotation whatsoever. And I remember one, a student like you guys, he was a bachelor. We had a good discussion. He said, no way, it's a solid piece. Everything is not possible. I said, no. Here, you have no rotation at all. Here, you have more. Never. On the equator, it's amazing. So what I did, I invented this. Look at this. See, this is going 12 times. That is going only 1 time. This is, and we're going like 3 times. See how slow that one goes on the North Pole? See, the reason why this has to travel more. And now, we are in Denver. In Denver, every second, 291 meters we are advancing. Well, of course, you need a frame of reference. Where? If you compare it, if you have a frame of reference, this is how we are going toward the east. See what happened? Well, of course, this is a small scale, but it doesn't matter. It works the same way. You see how fast that one goes? See, this one is slower. So this is showing exactly, if you're in the equator, it goes 465 meters per second. Well, when you're here, it's almost done. So what was the photo did? He was here. It's almost like Denver, almost like Denver. But I know there is one in the South Pole, but it's only for scientists. If I had a pendulum here, it is going to be independent. It's not going to do anything. It can swing back and forth. The reason why we have here, like I'll show you in a minute, because of deflection, because of Coriolis effect. See, the easiest way to understand it, just because we're talking about planets, you have all seen merry-go-round. There are 2 kids sitting on a merry-go-round. I'm throwing balls, and then he or she is throwing balls to me. We can catch easy. But see, what happened, that merry-go-round is going with the Earth.